All right, we're going to start looking at some applications of second-order differential equations. And we're really going to focus this time on this one mechanical application, mechanical vibrations. There are many, many others, all sorts of things ranging from electrical engineering to, of course, economics and physics and epidemiology, all sorts of things that you can use second-order differential equations for, but we'll use one common application here by looking at mechanical vibrations. So we've seen this picture before. This is a shock where you've got a spring and a damper sort of integrated together into one piece, but sort of the general, maybe more abstract setup looks something like this, where there's some mass on the end of a spring. And here's sort of a picture of a spring. Now, instead of drawing that, you'll often see something drawn like this to indicate a spring. Of course, if you're an electrical engineer, you'd think that looks like a resistor, but in mechanical engineering, that's a spring. So we've got some mass here, and you can measure the mass of the object, and we'll call that M. Then the spring will have some stiffness, and if you've seen this before, we won't go into it in great detail, but in Calc 2, for instance, you probably talked about springs and their stiffness, which we generally call K. This is the same stiffness that you see in Hooke's law, for instance. If you look at Hooke's law, which says that the force exerted by a spring is proportional to its displacement, and that proportionality constant is K. And of course, that force acts opposite to or in the opposite direction of the displacement. So if it's stretched out and the displacement is positive, then the force would be in the opposite direction, counted negative, or vice versa. And then there's also a certain amount of damping. And the idea of this damping is that it basically slows the vibration. It's essentially like friction on this vibrating object. And so we're going to call this B. B is a certain amount of damping, and this value of B controls how much friction there is in this problem. So kind of think of that as friction. Now the idea is that if we look at this object and think about the forces acting on this object, we're going to neglect gravity for the moment. Of course, you could add that in, but it doesn't really dramatically change the final setup. It just sort of adds a constant to the problem, which doesn't really make it super interesting. So the forces on this object, if it's been displaced by a value of y, so say we measure here from this equilibrium position, which is where the object would hang naturally if nothing is acting on it. And if we measure y from there, and we can measure y upward or downward, it doesn't really matter for our purposes. Let's say we measure it downward. Again, doesn't matter much for the formulation. The forces that act on this, again, neglecting gravity, you've got the spring force, which is going to be, again, opposite to the direction. So if y is positive, it will be negative. If y is negative, it'll be positive. So it'll be the opposite of y, and it will be based on that spring stiffness. So the force of the spring, we'll call F sub s, equals negative ky. So again, that's Hooke's law. The negative is there because the force on the spring, or the force that the spring exerts, rather, is opposite to the direction of displacement. So y is the measurement of displacement. You have the force of the spring, and then you have the damper force. And we won't spend a lot of time talking about this, but basically the idea of a damper, if you've ever used an air pump, for instance, like a bicycle pump, kind of gives you a sense of how this thing works. If you push down on it very quickly, it resists you more strongly than if you push slowly. So if you slowly compress a bicycle pump, you don't get as much resistance as if you compress it quickly. So the key to that is that the damping is proportional to the speed at which it is compressed or stretched. So it turns out that the damping force is negative by prime. So it's proportional to the speed or the velocity of this object as it moves. Again, notice the negative because, again, the damping force resists in the direction of travel. So if you are moving upward, it's going to push downward. If you're moving downward, it's going to push upward. So both of those forces act in opposition to either the displacement or the speed of the displacement. And so those are the two forces that this thing feels, again, neglecting a gravitational force, and then there might be some forcing function. So some external force, maybe I'll say it that way. An external force, we've called it a forcing function in the context of the differential equation. That's exactly what it'll be in the end, but some external force, let's call this Fe, which we're just going to call f of t. So some force, it can be whatever we want, and we'll leave it at that. So then we set up Newton's second law, which controls the motion of this. And Newton's second law, if you assume that mass is constant, Newton's second law says that F equals ma. If mass is not constant, we would need to add a term to that, but we're not going to deal with that at the moment. So if mass is constant, there's Newton's second law. So what that means is if we add up all the forces, that should be equal to ma. To make this more familiar, I'm going to replace that a with y double prime. And then I'm going to add up all the forces on the other side. So over here, I'm going to have negative ky minus by prime plus f of t equals m times y double prime. And then to make it more familiar, we're going to move these pieces over here so it'll look more like the ones we're comfortable with. And then I'm going to swap the sides on the equation just, again, to write it in the way that we're familiar with writing it. So what this boils down to is my double prime plus by prime plus ky equals f of t. So there's the second order differential equation that describes the motion of this object on a spring. And by the way, if you think about this object on a spring, you may think that the applications are fairly limited, but it turns out that lots and lots of physical objects that you may not think of as springs, you can model this way because every material has a certain amount of springiness to it, a certain amount of flex to it. And you'll look more into that in your further classes if you take other mechanical engineering classes along the way. So the key is that there's our second order differential equation that controls the motion. And we can talk about using different forcing functions here. We're actually not going to worry too much about that in this lecture. We know how to solve that using either undetermined coefficients or variation of parameters, or you could even use Laplace to solve it. But for now, we're going to leave that alone for now. And we're going to focus more on these three parameters, m, b, and k. Because it turns out by varying these values, you can dramatically change the behavior of the system. So that's kind of going to be our focus, is the behavior of the system as we vary m, b, and k, and how that's going to change things. Now, there are four categories of vibration that are controlled by these values. So we can talk about four categories of vibration. We're only going to talk about two of these, the first two. So you can have what's called free undamped vibration. The idea of being free is that it doesn't have a forcing function, which means f of t equals 0. And then the undamped idea means there's no damping constant, so b equals 0. And we'll look at what happens under those conditions. That's kind of the simplest of the four possibilities, is that there's no damping and there's also no forcing function. And we'll look at what happens to the motion of this object as it vibrates. Then you can still keep it free, meaning f of t is still 0, but you can have it be damped. And we'll talk about different options with damping. Basically, there will be a couple of different possibilities for how much damping there can be, and we'll talk about those in some detail. The other two that we won't talk about would be forced both undamped and damped vibration. And the reason we're not going to talk about these is that they don't add that much to this discussion. They're a little bit more complicated, so they kind of make the algebra worse, but they don't teach us a lot more that is super interesting at the moment. So we won't take the time to do these, but as I mentioned, you could use undetermined coefficients or variation of parameters or even Laplace to solve one of these if you would like to. So we won't spend much time on those or any really, but just recognize that if you understand the cases 1 and 2, adding a forcing function just changes it from a homogeneous equation to a non-homogeneous one, which means you need to use one of the non-homogeneous methods we have. So that's going to be kind of our layout. We're going to look at these two types of vibration, and we'll focus on them each individually.